Hello. In this video, I would like to give you an overview of the power series approach to understanding analytic functions. Originally, I had planned a larger section on this power series, but it's about 2 weeks worth of material, which the time we don't have. So I'm going to list the highlights of what we would have covered if you had more time. And hopefully this will act as an inspiration to dig into this very interesting material when you have more time on your own. Okay, let's jump right to it. Okay, overview of power series representation. So just a review of infinite series. If we have a sum from k equals 0 to infinity of some sequence ak, that's the same thing as taking the limit of these sums, and we're assuming the sequence to be in complex numbers here. We say converges if the partial sum has a limit as a sequence, right? So we've already shown what it means to have a limit. So when we write this, for infinite series as k equals 0 to infinity, we mean take this limit. If it converges, then it makes sense. If not, then we'll just say that it diverges. Okay. If you already are familiar with convergence in terms of real infinite series, then you could say that the complex series will converge if and only if both the real part and imaginary part taken separately both converges on their own. And we could also say that the series converges absolutely if the modulus has the series of the modulus converges. Okay, let's review a very important series. So let's say we're taking the sum of z to the k, and the power k is increasing from 0 to infinity for any complex number z. So partial sum would be adding 1 through z to the nth power. If we multiply each of the terms with z, then we get almost exactly the same partial sum, except we don't have a 1, and we have one extra term at the end, z to the n plus 1, instead of ending after adding z to the n. Since most of these terms are the same, if we take the difference, take Sn and subtract z times Sn, we get the 1 that was in the first series, and we're subtracting z to the n plus 1, which was the extra term that we're subtracting. Okay. But if we can write it this way, then we could actually solve for a very compact form of Sn. We could factor out 1 minus z from the left-hand side and divide. And we get partial sum is equal to 1 minus z to the n plus 1 over 1 minus z. This is great because it's easier to take the limit. We just have to look at the numerator, what happens as n goes to infinity of z to the n plus 1. So we know that if we're taking larger and larger powers, the behavior depends on the modulus. So if the modulus is strictly less than 1, then the numerator goes to 0. If it's strictly larger than 1, then the numerator will blow up and this will not have a limit. Right? But in the case that it does converge when the modulus of z is less than 1, then this is what we have for the limit. So that z to the n plus 1 will just go to 0. We're left with 1 over 1 minus z. Okay, so this is geometric series. And if you've seen it for the real infinite series case, it's exactly the same formula, except now we're thinking of z as a complex number. And in the real sense, maybe you have learned that it converges for value x between -1 and 1. It actually converges for any complex number with modules less than 1. So it converges inside of unit disk. Okay, so let's talk about power series. So power series is a little bit more general than the geometric series that we looked at. We are looking at different powers of z, but instead let's center it at z naught, not at 0. So we're looking at z minus z naught and looking at different powers of that. And we're allowing different coefficients to be multiplied for each power. So this is a much more general type of infinite series. If we're talking about power series, this is something that I need to point out. Usually 0 to the 0th power is undefined. But in the context of power series, if you plug in z equals z naught, which you could do here, then we'll get 0, and we're looking at different powers of 0. When we're looking at positive power of 0, it's clear it means 0. But if we're talking about power series case, 0 to the 0 is going to be considered to be 1. It's just the 0th power term is understood to be a constant. And we're kind of looking at power series as something that looks like a polynomial, where the power could go higher and higher. So it's like an infinite order polynomial. And we want that 0th power to be the constant term. So that's the convention. Okay, so let's write down a theorem. So if for any power series ak z minus z naught to the kth power, there exists some power, some radius r, so that series converges absolutely inside this radius, and series diverges outside of this radius. So actually, anything could really happen on the radius itself. If z minus z naught is exactly equal to r, it's possible that it could converge, it could diverge, it could converge not absolutely. It could converge for some values and does not converge for some other values. So in any combination of these things could happen. But if you're within the radius, it always converges absolutely. And outside of the radius, diverges for sure. So if you find this r, and if this r happened to be positive, so it converges for some disk, then we say that this is the radius of convergence. Okay. And I guess I said this already, but no general results for modules exactly equal to r. So it could converge, it doesn't have to converge. Okay, so these power series always converges inside of a disk. All right. So let's say you have a power series with some radius of convergence r greater than 0. Then looking at this power series as a function of z, it is analytic. And not only it's analytic, you can write down what the derivative should be. The derivative is exactly equal to this expression. So you're taking derivative term by term by using power rule. And you start to sum from 1 instead, because the 0th term, the constant term, becomes 0 when you take the derivative. Okay, so this is kind of nice because we know the formula for the derivative and we don't have to do anything fancy. We just have to know the par rule. So power series are analytic functions. So this is our connection to the rest of the things we know about analytic functions. Okay. And another thing that we can kind of get out of this is that we can actually write down all of the coefficients that you must have. Because if we take the derivative and plug in plug in z naught, we know what the AK would have to be. And we could take derivative as many times as we like. We just keep using the power rule and show that the kth derivative evaluated at z naught is the kth coefficient times k factorial, the k factorial coming from the power rule. And if you actually just kind of rearrange this expression, we can write the coefficient of the kth power must be the kth derivative evaluated at z naught divided by k factorial. So what does this tell us? It tells us that if we have an analytic function, the power series way of writing that function is unique, at least if it's centered at z naught. There's no two different power series centered at the same point that converges to the same function. I hope that makes sense. Okay. So every power series is analytic. And the next result will show that if you're analytic, then you have a power series. And not only that, it can tell you about the radius of convergence as well. So if you're analytic on some disk of radius r, centered at z naught, then you could show that the radius of convergence is at least that r. So it could be larger because maybe it's analytic in a bigger disk. But if you're analytic there, you're guaranteed to converge in that disk. Okay. So this is a more precise statement. So if F is analytic on this disk of radius capital R, and then choose the coefficient such that we get this expression 1 over 2 pi I integral gamma f of zeta over zeta minus z naught k plus 1 d zeta. You already know from Cauchy integral theorem that this is very close to the formula for the derivative. It's missing k factorial in the top. So this will give us the kth derivative evaluated at z naught divided by k factorial. Okay. So I could have written it that way, but this is how I stated it. And also, I guess kind of the corollary is that because these coefficients makes no reference to which disk you were looking at when you were looking at the domain of this analytic function, this really means that it kind of has to converge on the largest possible disk in its domain. So that's I wrote that as a corollary. Okay, so what does this mean? You could actually kind of use this to your advantage. For example, so let's say we were looking at function like 1 over z. So it's not defined at the origin. And then we just pick some z naught. Okay. So if you know the value of z naught here and all of the derivative at this point, so you only have to understand this function very well at that one point, then we have a power series that converges on the largest possible disk that fits in the domain. So in this case, it will converge on the largest disk that hits the origin on the boundary, but it cannot converge on any larger disk because then it can't be defined on 0. This function kind of blows up to infinity near that. So that's kind of nice to know geometrically what's happening. If you have this function in the power series form, and you kind of get disappointed, oh, I can't understand what the function is going to be outside of this disk. You could actually understand everywhere in the domain as long as you're willing to take the time to look at a new power series. So this power series tells us all the values up to the edge of the circle. So let's just say you come very close to the edge. But look at the value here. Let's call this Z1 and all of its derivatives at Z1. So you can compute it because you have the power series at Z0. And then you can write down a new power series with the new center Z1. So then that guy will converge in a new circle right there. Sorry, the picture is getting busy and terrible. But now you have a new power series that gives you value of the 1 over Z outside of the original circle because it converges on a new circle that's the largest, centered at a new point, Z1. And it does it in such a way that in the overlap of the previous power series, they agree. It's the same function there. So you can repeat this in this technique called Analytic Continuation. You could go anywhere in the domain, and then once you come close to the edge of the circle, you look at a new power series representation of that analytic function and get a new domain. And then you could extend the part where the function is defined. So the restriction of only converging on a circle, you don't have to feel like that restricts, like you can only look at one part of the function at a time. Well, if you're willing to spend the time to do this continuation, to expand it one circle at a time, you can do that. All right, so I feel like I didn't do this section justice because a lot of the insights and understanding of these things comes from looking at the proof carefully, and I feel like it skipped all of it. But hopefully this inspires you to look at the complex analysis a little bit deeper, and I'll see you next time.